This is Tom's screen. The upper part here is Tom's memory. The memory has addresses 0 through to 79. Each location consists of a high word and a low word. In general, we put instructions into the high word and we put addresses into the low word. You'll see how this works in a minute. Here is a program counter. That shows you where the instruction is being fetched from in memory. So you'll see how a program executes, and you'll see the flow of control as the program counter indicates the various addresses that are being used for the fetching of the instructions. This is the keypad you can use for programming Tom. Has instructions in their mnemonics, in their shorthand form at the top, and the underlying machine code underneath. On the right you have an output area. It's just a simple printer icon. So here I'm going to do a very simple program doing a loop. I'm going to start by loading the accumulator with a value, and that value is going to be fetched from memory location 16, and into that location I'll just put the value 9. So we're going to start our loop with the value 9. Then I'm going to output that, which is just simply this instruction out. Then I'm going to subtract from it, so accumulator minus, and I'm going to subtract from it the number I'm going to store in location 17. So I'm just going to put the value 1 in there, so we're just going to decrement by 1 each time. And I'm going to check to see if that's reached 0. So there's a jump if 0, which is here. And if that's true, it's going to go to, say, memory location 10, which I've just chosen to be a little bit away from the program here. And into 10, I'm going to put the halt instruction. Now that's, if you like, one iteration of the loop, but we want to go back and repeat it, but we don't want to go back and reload the number 9. What we want to do is go back to address 1. So we're going to jump unconditionally back to address 1. We can now run the program. You have a choice of single stepping it, instruction by using the step key, or you can just run it, which is what I'm going to do now. Notice how the program has been shown by its machine code before it runs. You can go back to the mnemonic version. You can run it again by resetting the program counter by clicking here. Now, I mentioned the registers earlier. There's quite a few others. There's a status register, which will show you whether there's an arithmetical overflow. There's a stack pointer register, which is showing you how return addresses work in a stack. We're going to see an example of that in a minute. Other options include the ability to program interrupts, in which case you have a keyboard which you can generate interrupts from and then write an interrupt handler for that particular device. There's an output device which is memory mapped, which is over on the right hand side of memory, and anything you put into there will automatically appear on the output. So I'm just going to turn those off. Don't want the output device and we don't want the interrupts, but we'll stick with the stack pointer, and we'll show how subroutines can be written. So this is a program I'm loading which calculates a factorial. It starts off by loading accumulator with the data at 12. I'm just going to change that to being 4, so we'll do the factorial of 4. Keep it busier for a little bit longer so you can see the stack more clearly. And the stack of return addresses is going to grow here, and this is what's used to remember, if you like, for Tom to remember where to return to every time it hits the return instruction, which you can see at the end of each of these subroutines. And notice the jump to subroutine here, which jumps to this one, then there's a jump to subroutine there, jumping to that one. You don't need to know the precise details of how this is programmed, just want to give you this flavour of seeing how a stack grows. This is usually a eureka moment, especially because this is recursive, because it's doing the same routine over and over again. And of course, being able to see that the stack just has the same return address gives you that immediate ability to understand how simple this mechanism is, and there's nothing complicated going on here at all. So I'm going to run this. You can see the stack growing. Return address is 19 and then 39, and then as the stack unwinds, you can see how it goes through the same subroutine several times on its way back, if you like. Let's reset the program counter. Out of the views, there's logic gates, full adders, half adders, control flip-flops, and so on. These are the components out of which Tom is built, if you like, and there's memory, how memory works, how data is fetched from memory. These are all interactive. How an address decoder works, how 4-bit memory works, and the machine, the underlying machine. This is Tom's underlying machine, and you'll see that this is basically copied the program into here. And when we run this, it basically takes you through the cycle of machine execution, identifying the location. Various gates are opened to allow data to flow, and you can follow the execution of this round. It's an entirely mechanical process where the various pieces of data are allowed to flow from one part of the machine to another, just simply by opening the gateways, allowing it to flow down into the instruction operand pair, and so on. Then the operand is then used to identify that part of memory, and then that value, having identified that part of memory, will then flow down into the general purpose register, and so on. This gives a perfect description of precisely how the machine is executing each instruction. Okay, so that gives you a reasonable overview, obviously not hugely detailed, but you can see how simple programs are done, how more complicated programs, and how they're all represented in Tom's memory. Thank you.